Okay, so welcome to this fourth meeting in our group. This time we read it, I hope everyone read the paper on the learnability of fully connected neural networks. That is very big guys, Michael Jordan and Wayne. Okay, and here's my take on this paper. And just to let you know that I'm not an expert on this topic. But Jose asked me and said, you're an expert on this topic.
No, but you're an expert in non-convex optimization, and this is very much related to non-convex optimization.
Yes, but very different ideas here.
Yes, I know that.
So I thought it would be very easy to read this paper, and then I started, it took me a big amount of this working week.
I'm sorry for that.
Yeah, so I read this paper. So the idea in this paper, what they're doing, is kind of a very standard problem, which is learning from data by using algorithm called neural networks. So, and the idea is that we have some data set. So here we have some data set, and we have this data X, and then which maps to some values in Y. So here X is from some set, the subset of Euclidean space in d dimensions, and then we have some kind of and then this Y is kind of labeling the data. For example, saying if I don't know, patient has a disease or does not have a disease, something like this. Okay, and then the goal of this paper is to, or just of neural networks in general, is to find a function from some set, which we'll define this more formally on the next slide, but find the kind of the best neural network, which kind of approximates kind of the function from X to Y. Okay, and these functions are, I mean, this construction is a bit complex. Usually we have a kind of this input layer where we put the X, this will be one X variable, we put it into the network. There are many layers where we kind of try to filter out different parts of the filter out different parts of the information or something to get to some complex function that will give us this, approximately this, this label of data. Okay? So, and the goal of this paper is kind of a different than the last seminar. The last seminar we were studying kind of for each function, like how well can we learn, or if there exists for each function like f, can we learn any kind of continuous function from a compact set? Can we learn any such function by using neural networks? Or if there exists a neural network, it's going to approximate this function. But we didn't say anything about the kind of complexity or how you actually learn these kind of networks. So the goal of this paper is to find we'll find algorithms that find a good function f, and also to kind of study complexity, kind of how difficult this is.
Just one point. It is more about computational complexity, not the sample complexity.
So you mean like this?
So given in this paper, so given a data set, how complicated is the task of computation finding this f? So something like that. So the whole idea, I guess, is that there is probably some f belongs to that nm, to that set of functions or set of those architectures. And then how hard is to find, given a data set, how hard is to find the best f? Something like that. But then there is another valid question, is something like that. So what is the sample complexity? How many samples do you need to learn something, given some budget for learning? So these are two sides of the same coin. So computational complexity and sample complexity. So here is about, I guess, computational complexity as far as I understand.
Right? So I mean, at least in this paper we have n cell data, and we want this n to be huge, because then we want to use this kind of sampling. This is much smaller, because in the end the computer complexity only depends on the sampling, not the full data.
Yes.
Okay, we'll come to it soon. So just to summarize, so I'll just first introduce the problem, better explain the neural networks and the problem, and then we will study kind of agnostic learning algorithms. So meaning that this is algorithms that can take any data and kind of find the best approximation in terms of neural network kind of that solves this data in the best possible way, given some kind of a cost function. Okay, and in this part of the paper, we actually show the authors, they gave an algorithm that is kind of, if you look at the algorithm, is polynomial in kind of the dimension of the data. It's the dimension of the x variable in the sample size, and also in something like a approximation, kind of this epsilon here is the kind of optimality, kind of how far you're away from optimality. That actually show that kind of if you want to be kind of closer to optimality, then kind of we will kind of make this optimality criterion smaller. Then kind of we will be converging at an exponentially kind of higher rate. Okay. But then the next question in the paper, they say, okay, here we're learning from kind of a very general data. What can we do if we kind of study only kind of specific data sets? And the data is study here is something where you can separate the data by there's actually a neural network that separates the data nicely. Okay, study that later. And we show that in this case, we actually get something that is polynomial in dimensions, in n, number of data, sets of data, and also in the kind of optimality criterion. But here we have something exponential growth in how kind of well separated the data is. So kind of when the data is kind of very poorly separated, then we will have then it will be very difficult to solve. But when we have, for example, maybe data that is very well separated, then we can learn it quickly in polynomial time. Okay? And then finally they asked the question, okay, here we only found kind of two algorithms. Here we found kind of an algorithm that is polynomial in these variables and exponential in this. Here we found an algorithm that is polynomial in these variables and exponential in this. But then they ask, is this the best we can do? Or is it a stupid algorithm or not? So they try to argue that this is not a stupid algorithm because actually it does not exist. They show by given some particular problem, showing that for these particular instances of the problem, actually you cannot find an algorithm that is polynomial in epsilon and polynomial in also in kind of the separation parameter. Okay, so this is kind of what we're going to do. So okay, so there is the core network. Okay, this we saw before. Okay, so the goal of this paper is to kind of find kind of optimal. We want to find an algorithm that finds the optimal neural network of all the neural networks, which kind of for a given data learns the data. We say the neural network that learns this particular data in the best way possible, and hopefully that it will generalize well. But then we need some measure. I mean, there can be many different types of optimality. What's the best neural network? So here they introduce some kind of a cost function for each neural network. So and here we have a cost function. So we want to minimize this cost function or loss function. I think this is why I well. So for each function, each neural network, this will be a function in n. Then we want to kind of minimize kind of the sum of these functions, where this is the kind of a data times what we learn. So this would be something like I'm usually with something. If y is positive, if y is 1, then I want this to be positive. If y is negative, then I want this, for example, to be negative. So this function will somehow capture kind of if you have a big value on this, kind of a positive value, that should be very good. If you have a big negative value of this variable, that is not good, then we're not doing something good. So we're going to give penalty to these path values and so on. Okay, and then we study this class on neural networks. So, and this class is defined here. So I think this is just pretty standard definition where we define a neural network with m layers, which will be a function, which will be a sum of some weight of some other function. But this is some kind of sigmoidal function. It's kind of a should maybe like an fraction. I mean, in many cases, people choose some kind of function that approximates the sine function because we want, if this is positive, then we want this to be 1. If it's negative, this to be -1. But since the sine function is not smooth, we want something kind of smooth out the sine function. And then we have this kind of weight on different kind of how, for example, if we have one that is kind of maybe performs better than the other, then we want to put high weight on that one and so on. And then this is kind of, and this here R, this is kind of how it would be kind of the width of the neural network. And then, so if this go back quickly to the picture, this R would be the width. And then the M would be the depth, with how many layers we have. Okay, and then the assumptions. So actually, I think, at least they argue in the paper that, I mean, here we assume that there's, the weights are bonded. Weights are bonded in all cases. And actually they argue in the paper that if you don't have bonded weights, then it's very difficult to win anything. I don't know, maybe it's your experience or what do you think?
I don't know actually. The thing is that the theoretical results will collapse. That's it.
Oh yeah, you cannot do anything.
Yes, but it doesn't mean that in practice it's not working. In practice it is working. I guess. I didn't try, but the others that tried, probably they are working. In practice you don't have to have that limitation.
So in practice you don't have any limits on the weights, right?
Most of them works.
So most of the time you don't have any.
Most of the time we have, but if you don't put it, then it isn't working.
Okay.
But you always tune somehow your parameters such that this doesn't happen.
When you put a constraint, you have a tuning parameters, you need to play with the parameters and all that.
One of the tuning parameters is this bound, right?
Yes, for example, you put this constraint as a Lagrangian form in the objective cost, and you have a regularization parameter in multiplication. So you need to tune that parameter.
Okay. Okay, so at least for this paper, I mean, this is essential. Okay, so let's start by studying algorithms that don't care about the structure of data. They can take any data and they will perform well. Okay, so in this case, we're just trying to learn. We're given some data. We don't know anything about the data, and we try to learn. And we have some algorithm parameters. We have, of course, this parameter you mentioned here, which is the bond on the weights. We have t. This would be a number of iterations of the algorithm, and then we have this k. This would be something like a sampling. How big is sampling? We'll discuss this very shortly. And then we have another parameter s, which we should discuss. This would be something like a, in the actual neural network we generate this s. This would be kind of the width of the or number of neurons per level or something in the actual algorithm, in the actual network we create. But recall that maybe I didn't highlight it well enough in the earlier slide that the class, this class n of neural networks, it can't have any. So one thing is maybe important is at least this for this class, this this kind of number of neurons can be as big as possible. There's no limit. But actually by using some approximation theory, which we'll see later, one can actually approximate any network by using only S samples. So we discuss it in a little bit. Okay? So this algorithm works as follows. Before we go over t iterations, it's capital T. At each iteration we will take k points, choose them at random, and this random should depend on something like a, maybe I didn't highlight those well enough that we have some kind of importance weight on a different data point. So we take this, choose these points at random, okay, and then we create one neural network. This is from this class here of the neural networks we consider, and this is actually where I started to get very confused, and I started to read the paper. That okay, we choose this neural network, but we don't do anything clever. Or we just choose essentially we choose a neural network at random. So I mean, this is a bit maybe complicated, but after going through it very thoroughly, I mean, the idea is that we choose a neural network at random. Okay. So and we can go through the steps. It's kind of create so that we kind of create in a recursive way, so that Okay, if m is larger than 1, then we just go kind of with one level down, and we generate S networks. So this would be kind of the width of the network. We could create kind of S networks of kind of the depth, which have the depth below, kind of one depth smaller. Okay, and these networks are creating. Creating using the same program. So this is a recursive program, and these network of this create randomly also. So in the end, we are kind of just going one level down, creating something at random, going one level down, and creating something random, and so on. So in the end, what we have is actually we just have a random network. And then the idea is that we create T random networks, and then kind of the idea is that because for each, actually, if you look at how we create the networks randomly, in each case we create a random network from something which is parameterized by this box which is k dimensional, and k is the sampling size. And the idea is something that we know kind of in this box, we know how to approximate the best network. We know kind of in each of these boxes there's something like a best network, and we will cover all of these, or something, if you take a random point in this box of, let me just throw it, and then I'll throw it in the box. So idea, we'll go through it a little bit. So idea should be something like this. So this would be kind of two-dimensional, but in this case k is equal to 2, and this would be, let's say, this is 0 point, this would be b. So this would be this here would be b. So this would be okay. So this would be a box. So essentially, we're choosing a point at uniform random inside this box. Okay, let's say a point here, and then with some, we know that kind of this kind of set, or let's say a box around this point will have with some epsilon accuracy, let's see, actually use b epsilon accuracy, this will have a measure that is not 1. No, not 0, I mean. So there's some positive probability that we are inside this box. Okay? And we know that in this box there's also some optimal function, which and we know that we reach this optimal function with some probability. And then we we know that in each case, with some probability, with this sampling, we reach the optimal function. But then we use some approximation theory to show, we used some other theory to show that we actually just need to find the kind of a best function with respect to k points, because that approximates, because we only want epsilon accuracy, that approximates the true optimal function well enough. Okay, maybe it's not very clear, but we go.
I guess that just to make it clear, if you go back to the architect of neural network, no, actually that figure. So the main problem that we do have here is at the end of the day we would have a non-convex optimization problem, and how we can solve this. So just that is helpful because the main optimization problem, the main idea was from this. So the thing is that the equation that you had is actually something like that. Just imagine that the function that these guys will be represent is u1. So this u1 is a combination of everything here. So this is actually what this u1 would have. And then this has u2, u3, so as to say, and then us, I guess you mentioned, right?
Yeah.
So, and then what is now the value here? Now the value is, if you assume that this is the optimal one, this is just an assumption. If you assume that this is the optimal one, then what you can do is that, okay, if you write down can you please go to the next slide? Next slide, okay, here it is. So that was actually, if you replace that with S, then you will see that this is exactly the same form that you have. So you have this architect of neural network, 1, 2, up to S, and then you have Wj here. Just imagine that there is just one output point, and then this is W1, W2, up to WS, right? And then the summation here would be exactly like this. The thing is that you have an activation individual here. So you have, just imagine that this is uj, okay, or fj. Then you have a sigmoid function here, and then at the end what you can see is that this guy here, actually you don't need to make the box here. This guy is responsible for having a non-convex optimization problem, because if you have more than one layer, then you have these guys that you should optimize over, because here you need to, at the end of the day, you need to minimize some form, you need to find f, some form of this loss. And then once you write down the optimization problem, the object, actually here it is. So once you write down, then you will see that you have this f for individual layers actually. So you have this f, and this f will be a function of these guys, and then these guys, and then these guys, and all those guys will show it here. So they will be a product, they will be a product of this guy, and then these weights, and then these weights, and then these weights, and this is the source of this non-convexity. So what you can do is that if you can show somehow that instead of having, so if you look at individual layer like this, instead of trying to optimize over all this, just assume that somehow magically you have the optimal solutions. Okay? If you have the optimal solution, then you don't need to optimize over those weights anymore. You will replace U1 or this guy, instead of having this guy trying to optimize, finding the optimal one here, you just replace F star here. So there is no optimization anymore for this guy. The same thing for this, for this, for this, and for that. And then you can see that if you want to run this optimization to find just one layer, then that could be a convex optimization problem. So now if you go to the algorithm, then you will see that why they do have this recursive one.
Hossein, is it the back propagation?
No, this is not back propagation at all. This is not about back propagation. Actually, this is one way to somehow, an alternative way, I would say, to the back propagation. So here you will see that here you have a very nice optimization problem, convex one, and then this guy here is actually the optimal solution. So you see that there is nothing like W here. So that's why that they are recursively finding that. So finding the optimal solution on the first layer, then assuming that these are the optimal solution, now trying to find the optimal solution for the second layer, third layer, and then you can do that recursively. So what those theories will say is that if you do like that, then an individual step, this function that you are finding would be within a constant bound of the optimal solution. By optimal solution, I mean the optimal if you do this non-convex optimization.
As a whole.
Yes, exactly. So this is what you can show, and then some theorem on approximation theories actually would help that.
So actually, I think,
So this looks like one coordinate descent, right? Each block
Something like that,
Oh,
yes,
okay.
something like that. But the main novelty here is actually the use of those approximation theory tools actually. To show that the functions that you will find would be, first of all, there is a function for individual nodes, so you don't need to optimize over the whole history here. So there is a function, and then you can find this function within epsilon accuracy. So that is the main contribution actually. And then it's not that much hard. The thing is that you should know those theorems in complexity theory and approximation theory, and then combine those tools. That's it.
okay, so this here the for this algorithm they prove these results for complexity. So this, if we choose, this would be a sampling rate. If we choose that this 1 over squared epsilon, which would be the accuracy of 1. And this would be kind of how many layers we need, on each level. Okay, so this would also be like 1 over epsilon squared. And then this would be how many iterations we need. Okay, so then I actually show that, okay, for any p and any epsilon and delta, our algorithm, or this algorithm, will give as output some neural network, such that this network, the loss for this network will be bounded by the best minimal loss, the loss for the best network, plus some constant. This is related to epsilon. So you can choose, essentially you could choose for any epsilon, you can make this here an epsilon by choosing it to cancel out these parts of the separate one here. Okay, and this will happen with some probability, which is 1 minus delta. And then we can choose this delta as small as possible, but of course at some cost in the it takes us longer time to reach that solution. Okay, and then you actually show that the complexity of this algorithm is polynomial in the sample size, NP, this is the dimension, and also in this 1 over noise here, but it's exponential in the error, or in the accuracy, in how precise the solution is. So actually it has the exponential on here. So you can see that we have an exponential of 1 over epsilon in the power of 3 times 10. Okay, so and before going to the proof, here's a bit more on the intuition of the algorithm. So this is, I guess, a bit similar to what Hussein was discussing. So actually we show that in a single iteration, so here we're considering, so we are creating a T networks, and we want to show that each network is with some small probability optimal, or it satisfies this point with some probability, some positive probability. And to do that, we want to find out how good, when we take this sample of k points, we want to know how good, if we take the loss function, approximate the loss function by using only these k points. So, and then we get something like this. So this here is the approximation of the loss function when we use k point instead of n points. Okay? And then we introduce this parameter. This is I use it here also. So, because actually this function is one can write it so it's only a variable of this parameter here. So this would be f of x1 to f of xk. Okay? So this g is only a function of this one. Okay? And they actually show, or they don't show, it seems to be pretty well known, at least in this community, about this, what's it called, like Rachanter complexity. So they actually, this is a known result from in the literature, that actually this approximation, if you use this many points, then this approximation will be good enough, approximation of the loss function, provided that we choose k large enough. And this here should if we want to get the epsilon accuracy that is precise enough that we need for the proof in this paper. Okay, so this is the first part they show. Okay, and then actually in this algorithm, then I think it should be. Okay, so the algorithm we choose is a U. It uses a random vector U, and actually with some small probability, let me just go back to the recall algorithm. Let me try to remember this one. Okay, so with some probability, this here should actually be this here. With some small probability on the top layer, this U will be the same as these parameters, because this is k-dimensional. So this is a k-dimensional vector in this set here. Okay, we know also if we take this function of the true optimal solution, then that will be a k-dimensional guy here. So we know that with some small probability, this U we have chosen, it will be close enough to the optimal function. So this is the idea. So we know that if we map the optimal solution in this k-dimensional set, then if we take any random variable, uniformly random be chosen, then with some small probability our U is closer to this one. Okay? And then actually we know that the optimal function, we can write it, it's also a neural network. So we can actually write it, it should have this form here, but there could be this S. We don't know, this could be very, very big. So for the true optimal network, we know that it's a neural network, so it has this form, but the sum should be over probably much more points than just over S, but it could be something that we call error. So it could be huge. But actually, they use here to kind of prove the result. They actually use the result from approximation theory, which shows that it's sufficient to take S points, where S is related to 1 over epsilon squared. If you take S points, then you can actually approximate this kind of with this epsilon accuracy, which is sufficient for the proof. Okay, and then we need to do something else. Okay, then we need to connect what we actually get, kind of in the lower level, so what the algorithm produces, and what's kind of the optimal for what is kind of the lower level for the optimal solution. Okay, so then actually we show that with some small probability. I mean, this is just using some kind of recursive arguments, going kind of to lower levels where we're choosing something which is with small probability true, then with lower probability, but still positive probability in the level above, with some positive probability, small positive probability. This should be kind of sufficiently close. And then what we get in the end is that, okay, so we get that, I mean, this is our kind of network, this is what we kind of got, but this is related to the kind of level and low level. And that will be with some, it will approximately be this. Yeah, this by combining all this and combining different probabilities. This is the probability of this U being close to the true optimal, and this is the probability that kind of all the guys in the lower levels are also, we have managed to create in all the lower levels also kind of a good enough network. So then we combine all these and we get that G of what we produce with the algorithm is approximately the optimal with this probability, but this probability is very small. It's very, very small. But that's why we do T iterations, because we just do it enough times to make this arbitrarily large, because this is all independent, because we choose, I mean, this use all in an independent way. So then we can, just by doing it enough times, then we will make this a lot. Okay. So just to go a little bit more deep in the proof. So I mean, the proof is basically based on 3 lemmas. The first 2 lemmas are just telling us something about, if you take, for example, we have sampled from k points, then this tells us how good this approximation based on these k points is of the full kind of a loss function, where we have all the data, okay? So, and for doing this, the authors, they introduce something which is known in the literature, which is called what is it? I heard it here. It's called like Rademacher complexity theory. Okay, so this is something, it's called Rademacher complexity. So it's basically just this function here and some noise here. This is like -1 or +1, similar as here, but with equal probability. Okay, so and then this measure here, this quantity, it will give us something. I mean, it seems to be pretty standardly used. You know, you have much experience with this, Hussein?
This just shows that if you have one set of samples, like, let's say you want to approximate. Okay, you have n samples, okay, and then you want to have, with some algorithms, you want to find the empirical risk over that n samples. So you have a data set of n samples, and then you want to find the best function that maps, or g of f, that is defined based on n samples, okay? And now instead of applying that on n samples, now you want to apply that on k samples, where k is smaller than n. So what this essentially says that if you can learn something with this data set, if you randomly sample out of that data set, instead of having n, randomly throw away n minus k of them, okay, then you will end up to a smaller data set, And then now what is the difference that you can have? What is the loss due to randomly dropping some points? So this somehow says that. So try to characterize that difference. If you can say that there is no difference, then you can say that there is no point of having a huge data set. You can just reduce that data set, and then your error will be bounded by the right-hand side there. So this is the main idea of this. And then there are some other forms of inequalities like this. But this is a very famous one, actually.
Yeah, but I was actually wondering, I was trying to get the intuition, because why is this, so this variable is -1 or +1 with equal probability, so 50-50 if it, but like, I didn't get kind of intuition, like, did you get, do you have any kind of intuition into why we choose this, why this would be good to choose it like this, or why would you not want to choose it, for example, in a similar probability as the actual output?
Yes, but I guess it's a kind of the worst case analysis, I guess. Let me see. Honestly, I don't remember the intuition behind that at this point, but we can talk it offline, definitely. And then that will be interesting to see. But as far as I remember, it was kind of the worst case analysis. So the worst case things that you will see, and then you want, because you want to bound the error, you want to bound the maximum error that you want to have, you will see if you just throw some of your data, okay? And if you have this mentality, try to develop some measure that somehow measures that worst case, then you will end up to this +1 and -1. But at this point, I don't really remember why we needed to have +1 and -1 with equal probabilities.
One thing I think, I mean, it's similar to entropy or something.
Yes,
You-
yes, yes.
Then it's the worst thing you can do is to have kind of an equal probability.
Yes, absolutely.
So I guess it's something good to do.
But they're definitely related, definitely related.
Actually, I have seen such summations, and then I was, I mean, that epsilon i's were called Rademacher
Random variables.
random
Yes, yes,
variables,
they are.
and so
Yeah, they are actually, and that's the definition. They are actually called those random variables.
Okay,
But-
why do you call flip of coin random matcher? I mean, that also isn't like a polynomial or something. Why do I call it also a...
Because the way that they were defined was based on this. So in this framework, they are defined in this way to be able to define this RK of F.
But everyone else in the world calls it polynomial.
Yes, I guess so.
Okay, so, I mean, similar, I mean, so in this paper, they show that using this measure, this complexity measure, at least in this case, and a lot of this is based on standard result. I mean, it's just like we combine some results here and there, fit into this problem. Okay, suppose that, so suppose that our function h, this would be kind of the main part of the loss function, is Lipschitz continuous, and in this class, this is any class of function. It doesn't have to be for a neural network. This is any class of function. Then this class of function has the zero function which is always 0. Then actually we can show that, we show in the paper that kind of the worst case. Yeah, it's the worst case between the kind of for any function in our class, the loss function minus kind of this approximation of the loss function is bounded by this right-hand side. Okay, so in addition to this, they also show that this particularly for neural networks, which we are studying, then we have also another lower bound, which is saying that this complexity here, I mean we can write it also here, for neural networks is bounded by Q, and which is just I think this is related to some of the norm of the okay, but there's this some constant, and also K, which K is how many samples we use to do the approximation, and then also this kind of we had bound on the weights. Yeah. Okay, and this. Okay, I don't remember why I put this here, but at least this is how we choose the K. Let me see. If you put this K in here, so let's put. This also tells us, gives us intuition into why when we choose K, size of samples. Why this is the number of samples we choose, is because when you plug this into here, then, I mean, this would disappear and we just get an epsilon here. So I guess we could also just put here also b kind of b time b in the power of m, and then we'd only get a simple epsilon here. But I guess maybe that makes the notation more complicated. Okay, so this is
just one question. I mean, all these results are for infinite number of samples, right?
No.
Or
They are large, but finite.
To find
Finite.
out the number of samples is actually n, and
So-
then the complexity will be linear in n.
but in the very beginning you said that there is an assumption that n is very large, so I
Yes.
get.
so actually there's a difference. So here we have the data set. So and the number of points in the data set is n. So then we had also something else which is called how many layers we have in the neural network. So saying like in the class of neural network we consider this here kind of the size of each layer can be as big as possible. I mean there's no limit on how many. Kind of a class of functions. This can be any neural networks, but there's no limit on how many on the kind of size of each layer in the neural network. So this was what was not limited.
But then he was saying that the number of those guys can be somehow, if you choose the number of, if you put some upper bound on the number of those guys instead of being any arbitrary value of the infinity, being up to order of 1 over epsilon square, I guess, then you will be fine. Then you can also find another upper bound for that RK. So you have one upper bound that he mentioned, so you have one upper bound from that complexity theorem, and then you have another upper bound, and then you can also again bound this RK if you set that the number of those guys are now limited, but sufficiently large, of course.
So by still, I mean, this sufficiently large and these things, I think, then you have intrinsically assuming that everything is asymptotic. So the number of samples are very
the
large.
thing is that here nothing should be asymptotic, nothing needs to be asymptotic. It's not at all an asymptotic analysis. The thing is that the bound can be loose or tight, but you have those bounds, and then the bounds are not asymptotic bound.
Okay.
But definitely it won't work for n equal to 1, because there is another upper bound. Actually, you had that in your table in the next slide, I guess. Or so, no.
Let's see.
Yes, here it is. So you see, k is a function of q divided by epsilon square, and then k is a function of n. Actually, n is a function of k. Well, say k is a function of n, right? So k cannot be larger than n. Or it can be? No, it can't be. K is smaller than n, right?
Yeah, so because the underlying assumption is that n is very huge.
Yes,
so for any
exactly.
action we choose, this has to be smaller.
Exactly, because k should be at least this one. Definitely you would go for very small epsilon. So k should be very large, and then n should be definitely larger than epsilon. So there is something underlying that says that n should be sufficiently large, but doesn't mean that n should be infinity for those results to hold.
Okay. Yeah.
Okay. So this was kind of the first part I proved. It's connecting the kind of. I mean, just mentioned this connecting kind of when you use k sample points, how well it approximates the loss function. And then there's the other part of the proof, which is saying something about when we have some neural network, how many layers we need to kind of approximate that neural network. Because like recall that this kind of the number of neurons on each layer can be infinite. Well, not infinite, but it can have any size possible. So we didn't want, and this here we want to say something about how many. They argue here, or they show here, that we actually only need s number of points to approximate any neural network. Doesn't matter how big the width is, or how many neurons are in each layer anyway. Okay, so let's look at this. And after this lemma. Okay, it's saying take any neural network in kind of with any deep network with kind of m layers. Okay, and consider the sampling set here. Okay, then it says that this should be the output of the algorithm. I think I forgot to mention it. So if you just look at this bond here, then it's saying that this is the output of our algorithm, and this is the optimum, or this is not the optimum, this is just any neural network with M layers. For example, it works also for the optimal, but also for any other network. Then this bounds hold, so the distance between what we get and the optimal, or any neural network in this class will be bound by this with some small probability. Okay, and you can see that this is a very small probability because it's here's epsilon and here's exponential in k, and it's exponential in s, and this is exponential in m. So this is like going to be huge, I guess. So this is going to be very, very tiny, very small number. Okay, but at least what we have is that we know this bound holds with some possible probability. And I mean, then we can just do it enough times, and then with some probability, like it's a very, very many times, but then with some probability we get something good. Okay, so I recall that this here is just some kind of a parameterization of the function f in these points. Okay, so it's just saying because these k points, so this kind of short time for this. Okay, how to prove this? So this is actually, I feel like, I mean, this lemma is kind of the main lemma explained, because this one explains the proof. No, it explains the algorithm, I mean, why it works. So I include it here. So actually, here they prove it by induction. Prove the result by induction. So suppose that we have only one layer, okay? Then we want to prove this. Then we have, okay, then we can write this part here, right here. Okay, we can write by using triangle inequality. We can plug in here this u, then we can put it here. This is using triangle inequality. Then we get the sum of these 2 points. Okay, then you call that this u is our kind of random point, using a uniform random in the box. Okay, and actually here is where the algorithm kicks in, because in the algorithm we chose. So remember, algorithm minimizes this. This is what the algorithm is minimizing. Okay, so we know that it's minimizing this. So we know that kind of one copy of this is going to be larger than this part. So actually, if we just take two copies of this, then it's going to be larger than the whole part. So actually, then in the end, what we have is that this whole part is equivalent by a random number minus the kind of the parameterization of the optimal function, or our constant function. Okay. And then, okay, then it just show by using, I mean, it's just like a geometry. Just by, I mean, you can see this by just plotting, looking at that. Actually, the area of, kind of, if you just look at the area, you can actually see that the probability of having this. So if you use an infinity norm, this is just by using, I mean, we know the area of this. We can easily calculate this, and then we know the area of the total m times n box, and then we can, by using such arguments, we can show that the probability of this is going to be larger than this, with this probability. Okay. Okay, and then we connect here just the equivalence on our norms, because like when we have one norm, then we know that infinity norms is going to be bounded by square root of k of the 2 norm, and that's how we get it's the other way around. Yeah, okay. The 2 norm is going to be bounded by the infinity norm, and then we have, I mean, this bond will hold with some probability, and then we actually have this upper bond here with some positive probability. Okay? This is clear? Okay, and then when you want to prove this in higher dimensions, then we actually assume that, I mean, the lemma holds for m minus 1, and then they use something that's called, it seems to this also to be pretty standard result. So you were well familiar with this result.
No, I wasn't, but it's a very well-known standard.
So
I didn't use that.
when you wrote it.
No, no, I didn't use that so far, but it's a standard result.
Yeah, it seems to be very nice. Okay, saying okay, just for any G, there's a subset of any Hilbert space. So Hilbert space is just a space with some norm. Okay, and we know that for this Hilbert space norm, we have some bound on all the points in the set G. Okay, then so usually having this H is going to be infinity dimensional. So this is one of the reasons why this is interesting. So okay, then for any point in the convex hull, so this could be non-convex or convex, could be discrete points also. So any V in the convex hull of this G, we can actually, and remember this can be infinite dimensional. And then it's saying, like for example, I guess for our neural network, it's going to be infinite dimensional space. Then there is a point V. There's a convex hull, so it's a convex combination of only S points, and it's kind of the distance between our original point and our approximation point is bounded by this. And what's it? So you can imagine that, for example, in our case, we have some function. We have some optimal kind of best function or something, or fixed function we want to find and approximate. And this function is in an infinite dimensional space. But actually, this result is saying that we can approximate it by using S points, and we will get a good approximation. And actually, how good the approximation is depends. I mean, it gets smaller, and the number of points we use gets larger, and the rate of how small it gets is this kind of square, this square root here. Okay. So, and this is actually, I mean, this is the result of this. I mean, the earlier result was telling us why we choose k, the number of sampling, the way we did, and this result is telling us why we are choosing the kind of the how many neurons we use per level or layer. And this is the reason we're choosing S like we choose it. And you can actually see if we put an S like 1 over square root of epsilon, then we get something like E and epsilon. So this is kind of intuition. And to use this as well, here we have kind of our function. And to make it a kind of convex combination, then we need to divide by B, just to make sure that, I mean, this is just the same network, we will divide by B, just to make sure that these sums up to 1. Okay? And then we know it's a convex combination of these functions, of some functions. Okay? And we also know that this. So we actually know that the parameters of this function here are going to be smaller than the square root of k. And that's because this h is like the whole thing here. No? And that's because we made the assumption of the sigmoidal function and it maps to -1 and 1. So we actually know that each component of this variable is going to be -1 or 1. So when we take the norm, then it's going to be kind of, I mean, each part is going to be bounded by 1, and then we sum over all and take the square root. Okay? Okay. And then we can just use this. Then we have the first part of the result. Then we just plug this in here. And then we know that there actually is Vs with using S points. So, and that this here is our Vs, and we know by using this bound, we know that it's bounded by this. And so here, like I said earlier, this is how we choose S. We choose it so. Here is plugged in for S, and then we get this nice point again. Where this is this approximation. Okay. Let me just quickly call what we're proving. So we're proving that the network, the algorithm returns minus any constant function is bounded by this with some positive probability. Okay. So this is what the algorithm returns. It returns, or not returns, but at each iteration gives. it gives a network which looks like this. G is at this lower level. Okay, here now we use the induction step. This is saying, okay, we know that for any part in the lower level, any function in the lower level, we know that with some probability, for any function in the lower level, we know with some probability that G is, that this holds for what we get from the algorithm in the lower level with some positive probability. Okay. Here I've just put the sigma function, and because the sigma function is assumed to be Lipschitz continuous in 1, that's why we get this equality. And then, okay, then we get this by induction step. Okay, and we have this with some probability here, which you also get from the induction step. So this is just the probability that it just holds. Okay, then the next thing we need to do is we need to show that actually, I mean this combination, okay, next thing we're going to show is that, let me check quickly. Okay, so next thing we're going to do is that for this function, which is close to the optimal function, we want to show that if we use the same weighing on these G that we get from the algorithm, then actually this should be bounded by something, with some probability. Okay? And because we have the same weight here, then we can just take them out by using this norm, and then we just take kind of the minimum, no maximum, kind of the worst case for all of them, and then we plug in this bound here, and then we get this, and we get the, I mean, the power grows by 1 because this is going to be bounded by B. Okay, and then the final step is to connect this G to this here. Okay. So this is the final step. And, oh yeah, and then I mean the idea to do this is just the same thing we did in the kind of to prove the case when m is equal to 1. We just use the same ideas actually here. So we know that by using some geometric arguments, we can kind of, we know that with some positive probability, when we choose this U kind of in the lower level will be chosen close enough to this. Okay? And then we get this probability, which is actually the same probability. And then to get the final result is just to multiply this, because of the independent events. Then you multiply this and this. And then actually, and then by using some, and by doing the algebra, and we combine it and we get this form. Okay? Okay, and then actually the proof of the whole thing is just about combining these three lemmas. The first lemma tells us that the expected value of approximation function, in worst case, the expected value of the approximation function with k subgroups and the true loss function is bounded by this right hand side. And actually by using this Markov inequality, this kind of connects probabilities and expected values. Then actually we can rewrite this form, this here, into this form, where we say that the probability of this event happening is bounded by, being bounded by this, is equal to 1/5. Just by plugging in some numbers here and doing some algebra. Okay, so this is the first thing, first result we have. Then, okay, by using this is the kind of the worst case, then we can actually just doing some kind of plugging this one in here, then we actually get that by rearranging this here, then we get that the loss for our network, the network algorithm terms, minus kind of the approximation error. Shouldn't this be plus? This thing?
It should be plus.
Okay, this will be plus, not minus. Right? This one also should be plus. Okay. So I mean, it's just saying that we use the approximation function here, and we get a little bit worse bound. This is kind of where we have to increase the upper bound by this. Okay. Then by doing some small reformulation where we plug this one into here, and this one into here, then okay, it's just equal. And then if we, if you use again this result again for this kind of, earlier we used it for G, but now we use it for F, because this upper bound should apply for both what the algorithm gives us, and also for the constant function where we're trying to hopefully our optimal function. Okay. Then we actually get this from here. I'm just trying to recall where we got this one. Ah, yeah, okay. So actually, going from here to here, this is just like a very standard algebra, and they do is steps in the paper, okay. And then we get kind of 10 here because now we have done this 2 times. Okay. And then again we get this thing, and then and then here we by using this, like the third lemma that you just proved, and we know that this here with some positive probability, the probability would be PM, the probability PM. This here is more than something that is related to this. I don't remember exactly. You want to check with me? Responded by this. And then by using that this event and this event are independent, we get that with this probability we have this bound on the what we get from one iteration. Okay, but recall that this is going to be very, very small. This here is going to be very, very small. But then what we do is just we do this. We know this holds a small, very small positive probability. We just do this very, very many times, enough times so we know that we the probability 1 minus d at least one of our networks is going to be this is going to result in at least one of our networks. Yeah. Okay. So this is the first result of the paper. Then we are gonna
just one point about the first thing. So I guess that one of the greater thing of the first algorithm is that it's not exponential in D, which is the dimension of the data. That's a great news because instead of searching over all possible functions on those dimensions, it's not exponentially exponential function of that, but it still is an exponential function of k. So essentially what they're doing to me is that they are somehow mapping that d-dimensional, all the d-dimensional inputs to some k-dimensional inputs.
Yeah, and remember that k is equal to 1 over epsilon.
Yes, yes. So they are mapping, actually instead of, let's say not d-dimensional, but let's say n-dimensional input. So you have n different inputs, and instead of trying to search over n-dimensional space to find a function, but at the end of the day, what you will do, you will try to find, the best thing that you can do is that, not the best thing, let's say the worst thing that you can do is that try to find one function on n-dimensional space that separates all the data, right? Definitely there is a function, and the complexity of finding that function would definitely belong to exponential class. So probably finding that function is exponential in terms of that n, okay? But this is the worst thing that you can do. But what they are saying is that what you can do, you can be much more smart by somehow mapping those data from n dimension. Again, n is the number of datas, right? So instead of operating or trying to find or solving some optimization problem on n-dimensional space, you can do that on k-dimensional space, and with the hope that k is much smaller than n. And then again, I guess that their complexity is exponential in k still.
Yeah, but I mean, I also remember, I mean, they don't say in terms of k, they say in terms of epsilon, because k is 1 over epsilon squared.
Yeah.
So, I mean, because k should only depend on how good accuracy you want.
Yes, yes,
Yeah,
yes,
right.
yes.
Yeah.
It would depend, but yeah, totally agree with you. But if I just double check the complexity, well, yes. Yeah, for instance, if you look at T, and T, capital T, is the number of times that you need to run with the hope that one of them will be sufficiently good, with accuracy epsilon and with probability 1 minus delta, right? So T is an exponential function of K, actually. So it's 5 multiplied by 4 over epsilon to power K. So this is the choice of, their choice actually in equation 3. And I'm not sure actually if this is the best that they can do, or is there anything better we can do at the end. But the thing is that, to me at least, they are mapping the whole functions. They are trying to reduce the dimension of the search space. Instead of searching in n-dimensional data, n-dimensional space, they are searching over k-dimensional space, which is quite nice.
Yeah. And exploiting some manifold structure of the data as well. They're
Yes.
assuming that the data has some like low-dimensional manifold structure, and the dimension of this manifold is k. And usually this is something that they also use a lot in neural networks, in deep neural networks as well. Trying to exploit this, like the fact that the data, on the high-dimensional data, has a low-dimensional structure, and this low-dimensional structure is somehow part of a manifold.
Yes,
And this
but they're
dimension of
searching
the
for
mani-
those
Yeah,
k.
absolutely.
So they're randomly sampling out of those n-sample k samples with the hope that they can find the best k manifolds,
Exactly.
k-dimensional
Exactly.
manifolds, and then try
Where
to
k
optimize
is
over
much
them.
smaller than.
Yes, hopefully.
Exactly. Hopefully, yeah. Exactly.
But here k, as you mentioned, is a function of 1 over epsilon
Yeah, it is
squared,
exponential. It
which is
exponential, yeah.
still quite high.
Exactly.
So if you want a very bad solution, then you
Yeah, if you want a very bad solution, then you can resort to one-dimensional
Yeah.
data and then search for a
Yeah.
linear separator, perhaps.
Nice.
Yeah. No, but it's strange. I mean, it's strange that it's just this like random initialization somehow with
Yes.
some least squares.
Yes, yes.
That does all the trick. Actually, it's not some very smart, sophisticated.
No,
algorithm.
actually I was thinking that instead of doing that, what they could do, I'm not sure if that's very easy to analyze, of course. The good thing with this analysis is that if you do that randomly, then you can simply say that whatever the probability was, now if you do that t times, then the probability that you will, all of them would
Yeah.
not be within that very, as you
Yeah.
mentioned, it's very small,
Yes,
non-zero
small.
probability. You will find some good function, right? And then you can do that over and over and over, and then the probability of finding that would be increased and increased and increased.
Exactly.
Or let's say the probability of not finding that would be exponentially decreased, okay? It would be 0.99999, but then you have an exponential decrease of that function. After some point, the probability of not finding the best function or the good function would be smaller than whatever threshold you have, and then you will be happy. But the good
Exactly.
thing, another way of thinking to this problem is that perhaps you can, so once you know that the data, if you look at this k manifold, then the data will look like, or this error will be much better than if you look at some other k manifold. So definitely there is a difference between these two. So then you can probably tune your search algorithm. So instead of trying to rerun this algorithm t times with independent sampling, then you can somehow improve your sampling for sure. But then the
Right.
problem now would be that those PM
Analysis,
that
yeah.
Sindri mentioned would be dependent over the
Exactly.
time. And wow.
Yeah.
Those PMs would be dependent, and then probably the analysis would be much
Right.
harder.
Yeah.
What
Exactly.
was that?
What was that?
I don't know. Anyway,
Right. Yeah.
but probably the actual complexity is much smaller than this. But the good thing is that, the stronger thing is that this is polynomial in D and N.
Exactly. Yeah, and this is just the strength of the work in the sense that it's a first result and it's a very strong
Yes,
one. Yeah.
it's still but exponential in K.
Yeah.
And then probably K would be in order of D. So it is not equal to D, but it could be, it's not equal to N, but it could be half of N or something like that.
Exactly. Or something also interesting to investigate as well would be to
Yes.
think about how tight are these bounds actually, because most of the proofs that they have are based on bounds, of course.
Probably
It would
not.
be Exactly.
Probably
exactly.
not.
Exactly. Yeah. But then how to tighten those bounds. So then the next
Yes.
question is is there a way to tighten the bounds?
Mm,
Yeah.
okay.
Yeah.
So this is the first part of the mission. So actually, just to be honest, I spent most of my time on the first part. I didn't have much time.
I guess that we don't have that much time yet.
I don't actually have so many slides on the rest because I just did this quickly in the end. Okay, so now we make some. So earlier we assumed that there's no constraint. There were no constraints on the data set. Okay, and we got results. Okay, but of course, if we know something about data set, we hope to be able to say something, get some better algorithms, and get some better results. Okay, so what seems to be kind of a standard assumption in the literature is what is called gamma separable data set. So I guess you have seen, maybe if you, I think it's pretty standard in machine learning to have some kind of a, for example, linear separable data set. So for example, when you know that there exists some line in your data set that kind of separates the two classes. Remember we have two classes like +1 and -1. Okay, but here we have something a bit more general. Because it doesn't have to be a line, it just has to exist some function in our neural network which actually classifies, which separates these two classes, where we have some kind of gamma. You can imagine gamma as kind of the area between or something like this. It's kind of how well they are separated. Okay, and for example with general function we could probably create a circle around, for example, this data set or something like this. You can separate more complicated data. Okay, so, and this algorithm uses, I don't remember what this idea is called. It's called like it's called boosting.
Yes, it's
Yeah.
auto boosting.
Auto boosting, yeah. And the idea is basically we use the earlier algorithm. It uses kind of another machine learning algorithm kind of as a at each step. And actually, I think that they can use like even very bad classifiers, which are only do a little bit better than on average. And then by combining these in some smart way, they will hope to get something good. So what they do here is they use as this bad, or not the bad, but as this kind of sub learner or sub algorithm. This is the algorithm for the previous step. And yeah, like before we have some M layers, we have some delta, which is to be kind of related to with how much probability we get, we correctly classify the result. We have gamma, which is the kind of how separable the data is. We have number of iterations, we have the same one as before. We start by kind of creating kind of this zero function, which you know is inside our function class that we discussed earlier, and some parameter b. And then at each step, we generate a neural network where, we generate this neural network here. Where we have this kind of weights, then it's important weights. And remember we had these importance weights also earlier, but we didn't use them. But they were just in the algorithm, kind of in the loss function, but we didn't discuss them. And actually when I started to read that paper, I was like wondering, like, what's the point of this importance weight? But then when you come to this part, then you can kind of see that here we have something like the idea is something that we kind of train, at each iteration we will train, by using the other algorithm, we will train, find a neural network, okay? We will find these neural networks, and then we want to kind of, in the next step, we want to put high weights on the data that was not correctly classified before, and then we run the iterations again. Okay. Okay, so the basic idea is that we kind of iteratively use the earlier algorithm to create a neural network, and then we kind of linearly add them. The final neural network is going to be a linear combination of all the network you have, where kind of the newest one is always trying to classify best data that was not correct earlier. Maybe you guys can give some more intuition on this algorithm.
Actually, I'm not very familiar with that auto boost algorithm, but the main idea was exactly as you mentioned. So try to improve in every step the actual architect of the algorithm that we could have. the artificial neural network, sorry, that you could have. But this is what I know from this other books. But this algorithm is clear, I guess, from that description.
Okay.
Um,
And then I mean these weights, I think they, I mean they don't come, I don't think they came out with the weights. I think they are kind of they're from other papers. So they're saying like, how to-
yeah,
this is
everything here is from other papers, so they're just using these
yeah.
to say that if we have those a structure on the data set where the data set is gamma separable data, then we can use this algorithm somehow
Mhm.
and then achieve a better bound, better complexity bound. This is the main idea.
Mhm.
It's not about introducing a new algorithm. So their algorithm one is something a new algorithm, I would say. But this is not that much new algorithm. It's just a combination of the algorithm, a little bit boosting of whatever we do have,
Mhm.
or something like that.
Yeah, and this, for example, the weights they use. I mean, this is seems to be standard.
Jesus.
I mean, I spent some
Everything
time
is
trying to
standard.
figure out like why are they using weights like this, and then I just decided some other papers. Okay, so just to give the main results they have for this algorithm. So they say, okay, we are going to do this many iterations, and this many iterations. Okay, and then they show, and they introduce a constant, and this constant is going to be something related to complexity. Let's just look at this in a little bit. Okay, so first they study kind of what they call in-sample error. This is meaning just like we already have a data set. Okay, we have run the algorithm. How well does our algorithm work on the kind of neural network we end up with? How well does it work on the data that you trained it on? Okay, so and the result is that okay, this is just like the output of the algorithm. It says that okay, and this is kind of this should be positive if we have classified correctly, and this is saying that we can bound and this make it more larger than this gamma divided by 16. This gamma is kind of separable with some small probability. This is 1 minus delta, where the time complexity is kind of polynomial in N and P, and also in delta. But for the C, we have this parameter. I mean, it's related to this C, and this C will kind of grow when kind of the number of layers in the network will increase. It will, yeah, but this is not exponential. It's going to grow polynomial in these parameters, but exponentially in the kind of separability parameter. So I mean, you can imagine if you have very good data, then if you have very nice data, then maybe this algorithm will work very well. But I don't know what other algorithms will work well with very nice data. And so at least this will work well. And then as the the data becomes more difficult to separate, then this algorithm is can be worse than with an exponential rate. Okay, so this is just for the data we already have, but what do we have on new data? Now first, that's the most interesting question. How well can we classify new samples? Okay, for any data set of this size, let this be okay, let's say we train our algorithm with a data set of this size. I mean, it's where n grows polynomially with respect to some epsilon, which we define in a little bit, and log of 1 over delta. And all the samples are independent and with the same distribution. And they are, we know that they are gamma separable points. Okay, and this would be the distribution function for the data we have. Then algorithm will output a function such that if we get a new data point from the same distribution, then with probability, we will classify. I mean, this is saying with 1 if this is positive, or -1 if this f is negative. So then we will classify. This algorithm will be correctly classify our data set. So the probability is smaller than epsilon. Let's see.
That should be greater than epsilon.
Yeah.
The probability of having error greater than epsilon should be smaller than something.
No, but
Okay, so this is saying that it's wrong. We want the wrong to be smaller than
Yeah.
epsilon.
Yes. Since this is error, then
Yeah, no, with probability 1 minus delta. Yeah, I think that makes sense.
That's okay.
Yeah, because it's with
Oh,
probability
yes.
1 minus delta.
yes, yes.
So the error
Mm,
is
mm,
upper
mm.
bound by epsilon with probability like 1
Yes.
minus delta.
Okay, but so I'm just thinking okay, we know this. I mean, we have this inequality with this probability. I mean, this is the right way to think about it, isn't it? So I mean, know that our algorithm will be this good, but we have this. We can assure this criterion with this. Okay, so we can ensure this criterion that our algorithm will ensure that will with probability small and epsilon classify everything,
Mm.
and the probability that we get that kind of algorithm is 1 minus delta.
Yes.
And some time complexity also is similar to this one. Where we
Mm.
have, except here we also have this error in the complexity. Okay. So this was the result. And I mean the proof seemed to be basically just use kind of combine their kind of algorithm with some standard result on the kind of this up boost idea. At least kind of when I look, that was at least what I understood.
Me too.
Okay, so but in general, I mean, reality is not so nice. Often we have data that is not possible to separate. For example, here we have a data set where we have, I mean, this is clearly one data set, this is clearly one data set, but here we have a point that was actually labeled in the wrong way. Okay, so they also want to say something about it. I was just wondering, like, of course, maybe if you have a very complex neural network, then probably you can create a function that's like this. So it's kind of separate. But anyway, they include, can I want to a little bit more general structure. We're saying that, okay, we call data set eta gamma corrupt separable. I just created this to try to write this compactly, this notation. If there exists a gamma separable distribution, gamma separable data set, this data set, such that, and this is gamma separable, and notice the bar, this makes it different with this one. So, where we know that this y will be kind of correct, this probability 1 minus n eta, and will be kind of the wrongly labeled, so like here in this case we have something that is wrongly labeled with probability eta. This eta will become the probability of error. You got that? Then in this case we're getting a couple of assumptions. They assume that, I mean, the error has to be smaller than half, because otherwise it's just, otherwise this data set is probably give us no information, because if it's wrong more than 50%, okay? Then for these constants, this neural network, okay, so I mean, it's basically just, it makes a particular neural network. It uses the sigma function in a particular way. It chooses the number of points is chosen like this. It's polynomial. The size, the number of points should be chosen, so it's polynomial 1 over epsilon and 1 over delta. Then there is a polynomial algorithm. I guess it doesn't really say that it's the same algorithm, but I guess it's some instance of that algorithm that will output f, some neural network, so that we will correctly classify the probability, correctly classify.
But this is the error probability actually.
Yeah, probability. I think. I mean,
And I guess that whenever you say with probability, I guess here it means with probability at least 1 minus delta. That was why we were a little bit confused. So this is the error probability, and then that would be with probability at least something. So this is
at least 1 minus delta.
Yes.
Yeah, I think this is
Exactly.
one at least. Yeah.
exactly. So that is the probability of having a small error. Bounded means that the probability of having error is smaller than epsilon. So this is the probability of having a good, let's say, good y, good sign of x, good function, so as to say. Okay. So this equation that you have is the probability of finding some good approximation should be at least 1 minus delta, sufficiently high. So this is like that.
Okay. So then there's the final question of the hardness. And actually I didn't manage to go way deep into that part of the paper because I was going out of time. But just to give some intuition, I mean, in both cases they make a case. They essentially want to make a case saying that what we have already, these algorithms we can do, you cannot prove it. You cannot improve it much. I mean, you cannot you cannot improve it except by maybe some scalars or something. You can maybe lower some scalars or something, but you cannot get a very much better algorithm by saying that you cannot. I mean, this algorithm, any algorithm that solves this type of problem, it will be exponential in either the error, or how accurate we get, the accurate solution is terms of optimality, or in this kind of gamma separable parameter. Okay, so and to make this case, it is considered one network. I mean, usually, at least we want to say that. You want to make a case that no algorithm can solve this problem, and they can decide to find one instance of the problem that the algorithm cannot solve. So, and they create one instance of the problem, which is the computational network with two. Okay, where we have kind of these two layers. So let me just maybe draw it real quickly. We just have a very simple network where we have an input x, we have one layer, something like this, and then we plug it into this function here. Plug this input into one thing I was a little bit. Let's see, it's actually because one thing I was a little bit confused, like this max, this here function, max, it doesn't satisfy the assumption. Because the assumption had to be, it has to be like a...
No, it doesn't.
Lipschitz?
It should be Lipschitz.
The Lipschitz.
It's not the Lipschitz concept, but it should be between, the range should be between -1 and 1.
Minus b and b or -1 or 1?
Yeah, so at least, I mean, this would be the sigmoidal function. Like,
Yes, yes.
Right.
let's say,
But then if they assume that the input is bounded, then
Yeah.
the output is gonna be bounded. Maybe that's
that's also what I was thinking. Probably, I mean, they say like this would be something like, but they assume like the sigmoidal function would be from R or all the numbers to.
Yeah.
So minus one
Minus
plus
1, 1, exactly.
Yeah, but of course if you say you know that the input is bounded, you know this is not going to go very far because when you plug in X here, you know the V is also bounded.
Exactly.
So.
But do we have this assumption of having
Yeah.
This
Yeah, the
sigma
inputs
goes
are
to
somehow
1?
normalized. Yeah, or actually have a maximum norm or something.
No, we have just norm on W and X.
X,
Yes, yes, on W and X we have norm, so we have that norm of inner product of W and X, that's true.
But this is the bound on X, so X is the
Yes,
input.
yes, yes.
So
I'm just saying that I'm not sure if we do have any bound on sigmoidal function, sigma.
There's a bound actually if you look at under already defined.
Yes,
and-
yes,
and-
yes, yes, yes. So I guess that this would violate that bound actually.
But yeah, but of course, you don't care what happens for the sigmoidal function outside of this range we are considering. So, since I mean, we know that this is bounded, we know this is bounded,
Yes.
so we know, I guess we know that, let's say, let's say we put V, let this be kind of a real line,
Yes.
where we look at V and X. Okay, and we know this is bounded by 1, I think, this is bounded by 1.
Yes.
So I guess the whole thing is bounded by, will be in the range by, oh, this is bounded.
yeah,
So maybe, then he doesn't care what
Yes,
happens
yes,
here.
yeah, exactly like Cauchy-Schwarz or something. Yeah,
Okay?
right. Yeah, exactly.
Was this like a small thing I was thinking? And then he uses this.
But
so-
sorry, one thing, W is not bounded to 1, W is bounded to B, right? The bound on Q, as far as I can see, the bound on
but
Q
in
is
this, so actually, for this problem, he's considering where the bound is.
1.
Yeah, so for this particular problem.
Okay, Okay, okay.
Yeah.
assumes that P is
Then
1.
this max could be a segmental function. Okay.
Okay. This he chooses this loss function. Then he says okay, and he considers this kind of this optimization problem minimizing this function, and he actually shows that this, if you can solve this problem by using a probabilistic algorithm, then actually you will also solve this problem. It's called max2 sat. So which is NP-hard. So therefore, if we can solve this problem, we can solve an NP-hard problem. So this is also NP-hard. So and then he said that, and that's how he argues that there is no randomized polynomial algorithm in these three variables which satisfy the weights satisfy this bond here. And so we can find this approximate solution, because then we can also solve this max2 sat problem. This is not really difficult. Okay. And then he also actually, well, they construct a similar argument, just saying complexity for separable data, but I didn't include it here. I mean, it's just they use another problem. So this is what I managed to cover in the paper. So here is some thoughts on the paper that we can discuss. So the first thing I was thinking about in this paper, I was thinking about it in relation to the earlier paper, the paper we were looking at last week. Last week we showed that when we have when m is equal to 1, when we only have one layer, then we know that f can be.
N was 2.
Was m2 in that?
M
M was 2 actually.
was 2.
In this framework at least.
At least 2, because m equal to 1 corresponds to 1 layer per subtron, so it's a linear mappings.
Oh yeah, but actually, so in this framework at least, it depends on how you define it. If you define only if you define the linear mapping as one layer.
Yeah,
I guess that they have defined
define a layer.
Yeah.
No, but I guess that they have defined that, right? So they
Yeah, but
have
in this
clearly
paper-
defined n1 as just one layer, so input, output, and a linear mapping. And then n2 is once you have input, hidden layer, output.
Okay.
So the previous session we had at least m2.
At least m2.
At least m2, but m could be larger than
At
that.
least one non-linear block.
One hidden layer.
One non-linear with
Yes, one nonlinear could be
Okay.
hidden block.
Okay.
So I was just wondering.
Okay.
Okay, then maybe my point is not.
No, but should that.
Okay. So I was wondering, like, okay, the last time we showed that you can approximate any function.
Hmm?
Then I was thinking by using only 2 layers.
Yes.
You can you do that? Okay. Then I was thinking of what's the point, because the complexity here grows exponentially when you go to many layers. But by using one layer, then you will manage to approximate the same kind of optimal solution